Hello students, in previous lecture we have talked about the distance between point and set, diameter of set, distance between two sets, etc. With help of distance between 2 points we are going to define bounded subset of metric space. So let XD be a metric space then subset A of X is said to be bounded, subset A of X is bounded if there exists some positive number m greater than 0 such that d of xy is less equal m for every xy belongs to A. Or diameter of A less equal m. A metric space XD is bounded if d of xy less equal m for every xy belonging to X. As here we are taking definition for any subset, so it also holds for whole metric space X also. In discrete metric space, d of xy is 0 if x equal to y, it is 1 if x not equal to y, then d of xy is less equal to 1 for all xy belonging to x, and therefore discrete metric space is bounded metric space. Is bounded metric space. Okay. Example, if XD is a metric space, XD is metric space, and D star, D double star are metric defined for XR are matrix defined for X or XR as D star of XY is equal to, say, D of XY upon 1 plus D of XY for every xy belonging to X, and D double star of XY is equal to minimum of 1 comma D of XY for every xy belonging to X. Then D star of XY less equal 1 and D double star of XY is also less equal 1 for every xy belonging to X. Therefore, by definition, therefore, XD star and XD double star are bounded metric spaces. Are bounded metric spaces. So for any metric space, it is possible to construct the metric for that set which is bounded. Which is bounded. Okay. Now we'll take some examples from our recommended book, Metric Space by Pawan Kumar Jain on bounded sets. So take the example. So that let XD be metric space and X belongs to X. Then show that diameter of open sphere SRX is less equal diameter of closed sphere SRX less equal to R. Solution. By definition, SRX is equal to set of y belongs to X such that D of XY is less than R, and SR closed sphere is equal to set of y belongs to X such that D of XY less equal R. this implies SRX, open sphere SRX is subset of closed sphere 1. Now for any yz belonging to closed sphere SRX, d of yz is written as, by triangle inequality, this is a d of yx plus d of xz. It is less equal r plus r is equal to 2r and therefore for any 2 points this is true. Supremum of d of yz where yz belongs to closed sphere SRX. This must be less equal to r and therefore diameter of closed sphere x is less equal to r. From 1 and 2, we know that if A and B are two sets so that A is subset of B, then diameter of A is equal to diameter of B. By using that, diameter of open sphere SRX is less equal diameter of closed sphere SRX is less equal to R. Is it clear? So, it is too simple. Now, it proves that every finite subset of any metric space is bounded. Next example, every finite subset of a metric space XD is bounded. So let A is equal to say x1, x2 up to xn be finite subset of metric space XD. Finite subset of metric space XD. Take M is equal to maximum of d of xi xj, d of xi xj, where xi and xj belongs to A. Then d of xy must be less equal m for every xy belonging to A. I am computing distance between any 2 points, all possible combinations. There are n points, so what will be possibilities of choosing 2 points from n point, that is NC2. So among that, I am taking m to be maximum distance. As it is a finite set, therefore maximum exists. It is not necessary to take supremum. So this implies A is bounded set. A is bounded subset of X. Right? Too simple. Now we'll take next example. If XD is a metric space and A is an empty subset of X, okay, then for any xy belonging to X, okay, so let XD be metric space and A be an empty subset of X, then should add d of, what is our aim? D of XA is less equal d of XY plus d of YA for any XY belonging to X. For any XY belongs to X. So solution, for a belongs to a and xy belongs to x, d of xa is less equal to d of xy plus d of ya. There is no any restriction on choice of a, xy, and therefore your infimum of d of xa, where a varies in a, this must be less equal to d of xy plus infimum of d of ya, where a varies in a. As this relation is true for every a. Therefore, distance between x and a is less equal to d of xy plus d of ya. Okay, for any xy belongs to x. There is no any restriction on choice of x. Is it clear? We'll take next example. If xd is a metric space, then x belongs to a closure if and only if distance between x and a is 0. Okay, so let xd be metric space and a is subset of x. A is subset of x. Then x belongs to a closure. X belongs to a closure if and only if d of xa is equal to 0. I think in theorem we have proved this. In theorem we have proved this. Okay. So x belongs to a closure if and only if for every r greater than 0, open sphere about x contains some point of a. Contain some point of a. Is it right? If and only for every r greater than 0, there exists a belongs to a such that d of xa less than r. Now since r is arbitrary, therefore d of xa tends to 0 as r tends to infinity. R tends to 0. And therefore infimum of d of xa is equal to 0. D of xa must be 0. Therefore, infimum of d of xa, where a varies in a, this must be 0. Okay. If and only d of xa is equal to 0. So x lies in a closure if and only if d of xa is 0. There is additional part here. By using this, we should add, we show x belongs to x minus a interior, x belongs to x minus a interior if and only if d of xa is strictly greater than 0. D of xa strictly greater than 0. Okay. So x belongs to x minus a, its interior if and only if, what this implies is it lies in interior if and only if there exists r greater than 0 such that open sphere about X, intersection, this is nothing but A complement interior. A complement interior. A complement is not equal to, is contained in A complement. As this lies there, it lies there, means what will get? D of xy is less than, or for every y belongs to SRX contained in A complement. Contained in A complement, and therefore SRX intersection A, SRX intersection A is equal to phi, and therefore X doesn't belongs to A closure. Okay, if I don't leave this, if I don't leave D of XA, this must be greater than 0. In bracket, since X belongs to A closure, if I don't leave D of XA is equal to 0. So with help of this previous result, we are proving this one. Now we'll prove that or take it as exercise. What time? Okay. If possible, we'll complete this example. Let XD be a metric space. XD be a metric space, and X belongs to X. Phi not equal A subset of X. Then D of XA is 0 if I don't leave. Prove that D of XA is equal to 0. If I don't leave, every neighborhood of X contains a point of A. Every neighborhood of X contains a point of A. Let me check it. So what we proved for X belongs to A closure, if I don't leave D of X is equal to 0. If I don't leave, that is 0. Okay. So solution, the D of XA is equal to 0 if and only if X belongs to A closure. If and only for any r greater than 0, SRX intersection A is equal to phi, not equal to phi. Okay. If and only SRX contain for every r greater than 0, SRX contain a point of A. Now, if n is neighborhood of X, n is neighborhood of X, then there exists r greater than 0 such that SRX is contained in n. From 1 and 2, every neighborhood of X, D of X is 0 if and only every neighborhood of X contain at least one point of A. Okay. Or it's and therefore what will get? Therefore SRX intersection A is contained in empty set not equal to N intersection A. Okay. So from this, from 1 and 2, 1 and 2, d of xa is 0 if and only if every neighborhood of x contains a point of A, at least one point of A, at least a point of A. So with this example, I like to stop here and hereby this bounded set concept from metric space is over. In next lecture, we'll study concept of subspace of metric space, which is important, and also how openness varies in a given metric space and its subspace. That is also important, interesting thing to study. So till that, stay home, be healthy. Thank you for listening my this session. Bye bye.